Okay, so to draw your very own Wiggers diagram, again, we'll probably start off here with, of course, just providing our x and y axes. So you can see you're going to want to create relatively generously sized axes here. And we'll just make, let's see, we'll make 8 of these today, 8 axes. And so, of course, when we think of the variables that are depicted in the Wiggers diagram, we have left ventricular volume, we have left ventricular and or aortic pressure. We can have transvalvular velocity. So that'd be for aortic valve. ECG, heart sounds, ventricular thickness, and we'll add 2 more variables here, which are often evaluated here on these curves. One could be coronary perfusion, and then finally we will put aortic dimensions, just as an example of things that you can place on these, and it really sort of dissect what's going on physiologically and interpret data sets more meaningfully. So now we'll start off with left ventricular volume. Of course, initially what we have is starting off with sort of late diastole, as it is in most of these images. You have a period where you've got an atrial kick sort of towards the end of diastole, and then a phase of isovolumic contraction. And so what we'll do is, as we sort of draw this initial portion here, we will insert vertical lines running all the way through all of our graphs, depicting these key segments of the cardiac cycle. And of course, then we have a period of rapid ejection, followed by a period of isovolumic relaxation. So again, now we're going to put another vertical line here. And of course, that's the onset of isovolumic relaxation. Here's the end of isovolumic relaxation. And then we will have a period of rapid relaxation, followed by late filling. And so that collectively should look pretty similar to what you have in the slides related to changes in left ventricular volume over the course of a cardiac cycle. Now, when we look at changes that are occurring in left ventricular pressure and aortic pressure, as well as atrial pressure, you can see that if we start off with left ventricular pressure, very similar to our changes in left ventricular volume here, you can see that we have a period where we have a deflection in left ventricular pressure due to that atrial kick. We've got a period where we've got a rapid generation of tension, which is the period of isovolumic contraction. Again, then finally, ventricular pressure exceeds aortic pressure. We have the peak, and then rapid decline, and then return back to close to zero for the rest of diastole. Now, that gives us, again, a frame of reference to start to apply some of our other pressures on. And so, for example, now, as we've done left ventricular pressure, if we take a look at aortic pressure, if we start here, actually, where we know ventricular pressure needs to exceed aortic pressure at this point, we can actually just pick a point there, and we can just sort of draw our way back here. This decrement in aortic pressure, and again at this point in the Wiggers diagram is the point at which ventricular pressure exceeds aortic pressure. So there, you want to make sure that aortic pressure is less than ventricular pressure. And as depicted in our diagrams, you can see about halfway through, we end up having aortic pressure exceeding ventricular pressure in large part because of the reflected waves in the elastance of the aorta, and then we come back down, and then have, with the aortic valve closing, we have that dicrotic notch, and then a nice period here, right? And so again, I'm not so concerned that you're precise in terms of the relative phases of systole and diastole and the proportions. It's really physiological principles here. Okay. So now, finally, we're going to depict atrial pressure on here. Again, I think the biggest thing here is just that atrial pressure, certainly here during diastole, atrial pressure is going to be slightly higher than what we would see with regards to ventricular pressure. And then during the initial phases of systole, and actually I'd say throughout systole, we have relatively low pressures in the atria. And then as we go here, and as we discussed in lecture, I think the major thing is just that we have relative reductions in atrial pressure during the diastolic phase here, right? And so that, if we label these, pressure in aorta, pressure in LV, pressure in left atrium. Okay. All right. So I realize it's kind of small for the drawing here, but hopefully depicting the point accurately. So those are the three pressures that we're going to draw here. Then when we move on to transvalvular velocity at the site of the aortic valve. So again, now what you'll see is we're going to be realistically 0 here. Right, and then what we will have as soon as ventricular pressure exceeds the aortic pressure, we will have blood flow rapidly increase into the aorta and across the aortic valve, and of course come back down here, right? And as the aortic valve closes, and then we will be right there again until the cycle continues. Now ECG, so again, P wave over here is going to precede your atrial kick. We've got a P wave here, and then of course it's going to have a pause with the PR interval, and then we will have the QRS complex occurring right at the onset of isovolumic contraction, and then a good delay here until we have a repolarization wave here, and then this will go out here until we repeat. You can certainly label these as P, Q, R, S, and T waves. Okay. So that's pretty straightforward. When we're looking at heart sounds, then we will of course we can just randomly put these in here somewhat, and then connect the lines later. At the time that the atrioventricular valves close, you can see we're going to have the S1 here. So that will be the S1 sound, of course, with the aortic valve closing and semilunar valves closing. We're going to have the S2 sound occurring out here. S3 sound is going to be occurring late with that rushing of blood into the ventricles. And then the S4 sound, when evident, is going to be occurring coinciding with that atrial kick. And so if you do it like that, then you can just have a nice connect the dots of S2, S3, S4, of your heart sounds. Okay. Now, if you are asked to depict something that is normal, generally what you would do is just depict S1 and S2. And if you are asked to present something that's pathophysiological, then depending upon the situation, you may depict an S3 or S4. But you should know, of course, that for most individuals, what you hear in health is just S1 and S2 sound. Now, when we're looking at changes in left ventricular thickness, as promised in class, generally what I would do is I would say, what we want to do is ventricular thickness is reducing during these phases of relaxation. Okay, so I would depict it largely like this. And then during contraction, what you'll have are progressive increases in ventricular thickness that essentially inversely parallel changes in left ventricular volumes. And then as you return down with progressive diastole, you would just have something that looks like this. So when I'm asking you to depict changes in left ventricular left ventricular thickness, I think that's a very, very reasonable way to depict that. And I think it gets the point across physiologically. So I think that is very good. And if you need to augment these a little bit just to make your point, I think, a little bit clearer, then this style of creating this is conducive to post hoc improving. So finally, with these last two variables, when we're looking at coronary perfusion, for example, now if you recall back to our one of our earlier lectures with coronary perfusion, there we know that the predominant amount of coronary perfusion is actually occurring during that diastolic phase, because during the systolic phase, you're going to have increases in ventricular tension. Those increases in tension are going to be compressing vessels that are within the myocardium. It's going to reduce coronary flow. And so when you're looking at depicting perfusion occurring predominantly during diastole, again, these are just largely relative changes, so relatively high amounts of perfusion during diastole. And I would just suggest having a somewhat inversely proportional change in coronary blood flow during the systolic phase, which parallels changes in the amount of pressure that's being generated in the aorta, in the left ventricle, and then ultimately remaining relatively high during the diastolic phase. And I'd say conceptually that's about what I'd expect you to have an appreciation of. And finally, when we're looking at aortic dimensions, again, this is one that I think is just of interest, because certainly with aging, there are changes in aortic dimensions that have pretty profound implications for ventricular afterload as well as systemic blood pressure. And so when you're looking at changes in aortic dimensions, you can depict them as you do thickness, or as you would as just an absolute dimension. So as you would ventricular volume. So of course with aortic dimensions, we don't have huge changes in aortic dimensions, but during diastole, those dimensions are being reduced, and then they would increase roughly proportional in proportion to changes in pressure, and then they would go along here. So again, I think the major point here is just being that in a normal elastic aorta, that you're going to have an increase in aortic dimensions during this systolic phase, which is going to store potential energy in the aorta and allow for the evening out of the overall blood flow systemically during that diastolic phase, and also enable perfusion of the coronaries during the diastolic phase. So overall, I think this is a great place for people to start, everyone to start. And for the normal conditions, and I will subsequently post a separate video for depicting a pathophysiological condition in comparison to this on the other side. Thank you.